Welcome to AI and Machine Learning Deep Dives.
Great to be here.
Today, we're diving into a really fascinating area of AI, naive Bayes classifiers.
Ah, yes.
It's a method that, well, the name itself sounds almost too simple, doesn't it? Naive.
It does. But don't let the name fool you. It's a model that really highlights how elegant simplicity can be surprisingly powerful.
Okay. So it has these surprising strengths, makes it useful in the real world. Our mission today, then, is to sort of uncover why this seemingly basic approach actually works so well.
Exactly. At its core, it's a family of probabilistic classifiers.
Probabilistic, meaning assigning probabilities.
Precisely. It assigns probabilities to different categories, based on the features we observe.
And the naive part, you mentioned that comes from a specific assumption.
That's right. A very specific and quite bold assumption it makes about those features.
Okay, let's unpack this. What exactly is this naive independence assumption you're referring to? What does it mean for how the model actually works?
Well, the core idea is that, given a target class, the category we're trying to predict, the naive Bayes classifier, assumes that all the features are conditionally independent of each other.
Conditionally independent. Okay, what does that mean in plain terms?
It means it treats the information each feature provides about the class and entirely unrelated to the information from any other feature. It essentially says, okay, I'll look at the color, then I'll look at the shape, then the size, and it treats each piece of evidence completely on its own merits.
So let's take an example. If we're trying to classify, say, a fruit as an apple, right? And we look at its color, its roundness, its size. This model assumes that the color, maybe red, tells us something independently about it being an apple.
Yes.
And its roundness tells us something independently and so on. It doesn't consider that, being red and being round might often go together in apples.
Exactly. It completely ignores that potential correlation. It just sees them as separate, distinct pieces of evidence pointing towards apple or not apple.
That does sound, well, naive. It seems like a highly unrealistic assumption for most real-world things, doesn't it?
Oh, absolutely. In reality, features are often deeply intertwined. Think about it. Height and weight in people, they're clearly related.
Right.
Yet, and this is the fascinating part, despite this seemingly oversimplified design, naive Bayes classifiers have proven remarkably effective. In many complex situations, they perform really well.
That seems so counterintuitive, though. How can something based on what sounds like a fundamentally flawed assumption perform well? Why does it work?
Well, there's some solid theoretical reasons, surprisingly. One key advantage is its scalability. It's incredibly efficient.
Efficient how?
It only requires estimating one parameter for each feature, essentially. This makes training super fast. We're often just talking about counting observations in different groups.
Just counting, not complex optimization.
Not the kind of complex, iterative stuff many other models need, no. So it's fast. Plus, it generally only needs a relatively small amount of training data to get going.
That's a huge plus. Labeled data can be hard to come by.
It really can. And here's another interesting bit. The classifier can be quite robust, even if its underlying probability estimates aren't perfectly accurate.
How so?
As long as it correctly identifies the most probable class, it doesn't always matter if the exact probability value is a bit off.
Ah, I see. So it doesn't need perfect calibration. It just needs to pick the winner correctly most of the time.
Precisely. Think of it like it doesn't need to tell you there's exactly a 73% chance of rain. It just needs to reliably tell you, yeah, you probably need an umbrella.
Okay, that makes sense. It's about the decision boundary. So stepping back, how does it actually make a classification? What's the mechanism, the process?
At its heart, we calculate the probability of an item belonging to each possible class, given its specific features.
Okay.
And this relies fundamentally on Bayes' theorem.
Right, Bayes' theorem. Can you give us a quick refresher on that?
Sure. Simply put, it's a mathematical way to update our beliefs based on new evidence. It lets us calculate a posterior probability, our updated belief, by combining our prior probability, what we thought before, with the likelihood of seeing that new evidence if our prior belief was true.
And the naive assumption helps here.
It helps massively. It simplifies the calculation of that likelihood term. Instead of needing a complex joint probability, we can just multiply the individual probabilities of each feature appearing within that class, along with the overall prior probability of the class itself.
So you calculate this final probability for Class A, Class B, Class C, and then you just choose the class with the highest probability.
Exactly right. That's called the maximum a posteriori, or MAP decision rule. Winner takes all.
Maximum a posteriori. MAP. Got it.
And a common practical technique, just to mention it, is using log probabilities during these calculations.
Log probabilities, why do that?
Well, when you multiply many probabilities together, especially if they're small, the result can become incredibly tiny. So small that computers can run into precision issues, something called arithmetic underflow.
Ah, the numbers get too small to represent accurately.
Exactly. Working with the logs of the probabilities turns multiplication into addition, which avoids this underflow problem entirely. It's much more numerically stable.
Clever. Okay, so it sounds like there might be variations on this theme. You mentioned it's a family of classifiers. Are there different kinds of naive Bayes?
You've hit on a key point. Yes, there are. The specific way we estimate the probabilities or parameters for a features distribution depends heavily on the type of data we're working with.
Makes sense. Different data, different approach.
Right. These different approaches, these assumptions about the data's distribution, are often called event models.
Event models. Okay, like what?
Well, for continuous data, think of measurements like height, weight, temperature. We often use Gaussian naive Bayes.
Gaussian, like the normal distribution.
Yeah.
The bell curve.
Precisely. It assumes these continuous values within each class are distributed according to that familiar bell curve. So during training, we just calculate the mean and the variance, how spread out the data is for that feature within each class.
Okay, so mean and variance for continuous stuff. What about data that isn't continuous, like counts, word counts in a document, for example?
Good example. For discrete features like word counts, we typically use multinomial naive Bayes.
Multinomial.
Yeah. Here, our features represent counts like how many times a particular word appears in an email. Our samples are essentially frequency counts or histograms.
And that's common in text stuff, right? Spam filters.
Absolutely. Document classification, spam filtering, this is a classic application. It often goes hand in hand with what's called the bag of words assumption.
Bag of words, meaning the order doesn't matter, just which words are there and how often.
Exactly. The sequence is ignored, just the counts.
Okay, I can see a potential issue, though. What if a specific word, say mortgage, never appeared in any legitimate emails in our training data, only in spam? If we then see a legitimate email with mortgage in it, wouldn't the probability of that word appearing in the legitimate class be 0?
Spot on. That's a critical problem.
And if you multiply by 0, the whole probability calculation for that class becomes 0, right? Even if everything else points to it being legitimate.
Precisely. That's called the zero frequency problem, and it's a major pitfall. One single zero probability can wipe out an entire class calculation.
So how do we fix that? You can't just ignore words.
We use a correction. It's often called a pseudo count, or more formally, Laplace smoothing or Lidstone smoothing.
Pseudo count.
Yeah, the simplest form is add one smoothing. You basically pretend you've seen every possible feature at least once, even if you haven't in your training data. You add a small value, often just 1, to all the observed counts.
Ah, so that ensures no probability is ever exactly 0.
Correct. It prevents that zero multiplication issue and preserves the information coming from the other features. It's a crucial little trick.
Okay, that makes sense for counts. Is there anything for, say, just presence or absence? Like, is a word in the document yes or no? Maybe for shorter texts.
There is. For those kinds of binary features, present or absent, we often use Bernoulli naive Bayes.
Bernoulli,
Yeah.
like a coin flip, yes or no?
Exactly. Instead of counting frequencies like multinomial, it just looks at whether a term appears in the document or not. It explicitly models the absence of terms as well, which is a key difference. Popular for things like classifying short text snippets.
Interesting. And you mentioned earlier the challenge of limited labeled data. Can naive Bayes do anything with unlabeled data?
Yes, it can, through something called semi-supervised parameter estimation.
Semi-supervised, using a mix of labeled and unlabeled.
Right. It's usually an iterative process.
Yeah.
You start by training the model on the labeled data you do have.
Okay.
Then, you use that initial model to predict probabilities for all the data, both the labeled stuff and the unlabeled stuff.
I see. And then
And then you use those predictions, often weighting them by confidence, to effectively create more labeled data, and you retrain the model. You repeat this cycle.
so the model sort of bootstraps itself, using its own predictions on unlabeled data to improve.
That's a good way to put it. It's a form of the expectation maximization, or EM algorithm. It lets the model learn from the structure present in the unlabeled data, too.
That's quite sophisticated for a naive model. Let's try to make this more concrete. Can you give us a practical example? Walk us through one.
Absolutely. Let's use that classic example. Classifying a person as male or female based on some measured features, say height, weight, and foot size.
Okay, 3 features. Height, weight, foot size.
Right. First, we need a training set, a group of people where we already know their gender and these 3 measurements.
Got it. Labeled data.
Using this data, assuming Gaussian distributions for these continuous features, we calculate the average height, average weight, average foot size for the males in the set, and separately for the females.
Average. And the spread, too, right? The variance.
Exactly. Mean and variance for each feature for each class, male and female. We also calculate the overall probability of someone being male or female in our data set. Those are our priors.
Okay, so we have our parameters learned from the training data. Now what?
Now we get a new person. We don't know their gender, but we measure them. Let's say they are 6 feet tall, weigh 130 pounds, and have a foot size of 8 inches.
Okay, a new data point.
We then use our calculated parameters.
Okay.
We ask, what's the probability density of seeing a height of 6 feet, given the person is male, using the male mean variance for height? And what's the probability density given they are female? We do the same calculation for the weight, 130 pounds, and the foot size, 8 inches, comparing them against the male and female distributions we learned.
So you get likelihoods for each feature under each class assumption.
Precisely. Then, using Bayes' theorem, simplified by the naive assumption, we combine these likelihoods with the prior probabilities for male and female.
You multiply the prior by the likelihoods for each feature.
For the male class, and then separately for the female class. Whichever class yields the higher final posterior probability is our classification.
So for this 6 foot, 130 pound, size 8 foot person, what would the model likely say?
Interestingly, based on typical distributions, that combination might actually be classified as female.
Really? Even at 6 feet tall?
Potentially, yes. Maybe the weight or foot size relative to height is a stronger indicator for female in the training data the model saw. It shows how the model weighs each piece of independent evidence, even though we know these features aren't truly independent in reality.
Right.
The naive assumption often still leads to surprisingly good classification results in practice for this type of problem.
That really clarifies the process. And I know this technique is huge in text analysis. You mentioned spam filtering.
Indeed. Document classification is probably one of its most famous and, honestly, impactful applications. And yes, the prime example everyone encounters is spam filtering.
Let's talk about that. It feels like a never-ending battle, the spam wars. How do these naive Bayes filters actually work to tackle spam?
Well, naive Bayes spam filtering has been a workhorse technique, really. It dates back to the mid-90s and became quite popular by the late 90s.
A long history in internet terms.
Absolutely. It works by correlating the occurrence of tokens, usually words, but sometimes other things like phrases or even sender information with whether an email is known spam or known legitimate email, often called ham.
Ham, like not spam.
Exactly. So you train it on examples of spam and ham. It learns which words are more likely to appear in spam versus ham.
Okay.
And modern systems, things like Spam Assassin or filters built into Gmail, often use variants of these techniques. A big reason is they tend to have low false positive rates.
False positives meaning legitimate emails getting marked as spam. That's the really annoying one, right?
That's the critical one for user experience. You really don't want important emails disappearing into the spam folder. Naive Bayes tends to be pretty good at avoiding that.
You mentioned challenges before, like the zero frequency problem. How do spam filters handle words they've literally never seen before during training?
Right, the unknown word problem. Filters might handle this in a few ways. Some might just discard the unknown word, ignore it.
Seems suboptimal.
It can be. More effective approaches use that pseudocount or Laplace smoothing we talked about. They assign a small, non-zero probability based on some prior assumption or background knowledge about spam likelihood.
Okay, it keeps the calculation going.
Exactly. Also, filters typically ignore very common neutral words like the A is. They don't carry much signal about spamminess.
Stop words.
Right, stop words. Instead, the filters focus heavily on words whose calculated spamicity, the probability of appearing in spam, is either very close to 0, meaning distinctly legitimate, or very close to 1, meaning distinctly spammy. Those are the strong indicators.
So words like free, Viagra, offer on one side, and maybe more normal words on the other?
Precisely. Some advanced systems even look beyond single words. They might look at short sequences of words or patterns to get more context. Like the phrase click here might be more indicative than just the word click or here alone.
Makes sense. But spammers must constantly try to get around this, right? It's an arms race. What tactics do they use?
Oh, definitely. One common tactic is called Bayesian poisoning.
Poisoning. Sounds bad.
It is. Spammers will deliberately insert large chunks of legitimate-looking text, maybe copied from news articles or books, into their spam messages.
Why would they do that?
They're trying to dilute the spammy words. They hope the flood of normal words will lower the overall spam score calculated by the filter, letting the email sneak through.
Clever. What?
Word obfuscation. They'll transform known spam words, like Viagra might become V1agra, or Viagra or V-Digra.
Trying to make it look different so the filter doesn't recognize it as the same token.
Exactly. They hope the filter hasn't learned these specific variations yet.
So how do the filters fight back against poisoning and these word tricks?
Well, against word transformations, filters often learn these variations over time through continuous training. As they see more spam, they learn that V1agra is just as spammy as Viagra.
Okay, they adapt. What about the poisoning with legitimate text?
Some more sophisticated naive Bayes implementations are less susceptible to that. They might focus only on the most statistically significant words, ignoring the neutral filler text.
Yeah.
Or they might weight words differently.
I see. Less easily fooled by dilution.
Another tactic spammers tried was replacing text with images containing the spam message.
Because the filter couldn't read text in an image.
Initially, yes, but that has downsides for the spammer bigger email sizes. And many email clients now block external images by default for security.
True.
And guess what? Some major email providers, like Gmail, now use optical character recognition OCR to actually read the text inside images in emails.
Wow, really? So they can scan the text even if it's in a picture?
Yep, pretty much neutralizes that tactic.
Okay.
The arms race continues.
It really is impressive how this relatively simple classifier holds up, even with these constant attacks. But let's zoom out again. How does naive Bayes stack up against the more modern, often more complex machine learning models we hear about, things like boosted trees, random forests, even deep learning?
That's a fair question. In terms of raw predictive accuracy on some complex data sets, naive Bayes can be outperformed by models like gradient-boosted trees or random forests,
Okay.
especially when it comes to accurately quantifying uncertainty. Naive Bayes often produces probability estimates that are a bit too extreme, too close to 0 or 1. It can be overconfident, as we say.
So its probability scores might not be perfectly calibrated.
Often not, compared to models specifically designed for calibration.
So if there are potentially better models out there, models that don't make that big, naive independence assumption and might give more accurate probabilities, why do we still use naive Bayes so much? What's the enduring appeal?
Several key reasons. Its simplicity is a huge one. It's easy to understand, easy to implement, and computationally very cheap.
Speed and efficiency.
Exactly. It trains incredibly fast, often orders of magnitude faster than more complex models, especially on very large datasets like text corpora. And its efficiency with smaller datasets remains a major advantage when data is scarce.
Right, the low data requirement.
And remember, even if its probability estimates aren't perfect, it often still makes the correct classification. It finds the right decision boundary, and surprisingly well.
Good point. The classification accuracy itself can still be high.
There's also an interesting theoretical relationship with models like logistic regression. While logistic regression directly models the conditional probability and often achieves better theoretical performance eventually, naive Bayes, by modeling the joint probability and making its assumption, can sometimes converge to its optimal error rate faster, especially with limited data.
So practical simplicity can sometimes beat theoretical elegance, at least in terms of speed and data needs.
It's a fantastic example of that, yes. It's a testament to how a pragmatic, even if theoretically flawed approach can be incredibly effective in the real world. It's not just spam. Think medical diagnosis predictions, sentiment analysis from text. It's been a foundational tool in many areas.
It really drives home the point that the best model isn't always the most complex one. We've seen today how the naive Bayes classifier, despite that core naive assumption, has become this robust, efficient, and widely used tool in AI, particularly in text, like spam filtering. It's a great reminder, isn't it? Sometimes the simplest solutions are incredibly powerful.
It absolutely is. It really forces you to think about model assumptions versus practical performance. A model can be highly functional, even if its view of the world isn't perfectly accurate. And it does make you wonder, what other simple ideas might be out there, surprisingly effective against complex problems?
A thought to ponder. That's all for now, folks. Please like, share, and subscribe.